finding maxima and minima, right, the largest and smallest possible values, as is our goal in optimization, is all well and good. But when we go to apply these techniques to the real world, it is very often the case that we still want to find a maximum or a minimum, but we have some additional limitations to consider. And that's where the idea of constrained optimization comes in. Hello, welcome back to the Quant Plus YouTube channel. Before we begin today's video, I wanted to shout out those who are supporting the channel. I'm seeing some growth, I'm seeing some comments, I'm seeing some interactions, and I really appreciate that. In addition to what you've already been doing, if there are certain topics that you'd be interested in seeing, please leave them in the comments. That would be greatly useful information to kind of inform where some of my next videos will go. In terms of the topic I want to bring up today, the formal terminology is constrained optimization, and as we were alluding to earlier, it is essentially the idea of still finding maximum and minimum, maxima and minima, but we have some additional things to worry about, some constraints. In the single variable case, so let's discuss that first. The general steps would be to use the constraint to rewrite the problem in terms of a single variable, and then really apply the same techniques that we were using in terms of finding the derivative, setting it equal to 0 for finding critical points, and then making sure that the second derivative is positive if we're finding minimum, or second derivative is negative if we're finding maximum. And here I have an example for you. Suppose that we have a box where it's a rectangular box where the bottom of the box is a square, the base of the box is a square, it has some height, and it has an open top. We know that we have 120 square meters of material that we can use, and we want to find the box that has the largest possible volume. Well, let's kind of work with what we have here. The first thing that we know is that volume is the area of the base times the height, and in our case that's going to be s squared times h. We also know that the surface area as it's being described in this particular scenario is surface area is s squared plus 4sh. Well, from here, if we say s squared, let's write that a little bit neater, s squared plus 4sh is equal to 120, then we can write 4sh equals 120 minus s squared, and h is 120 minus s squared over 4s. So writing this in a slightly simpler way, this is 30 s to the negative 1 power minus 1/4 times s. The key idea here is that now we can rewrite our volume formula instead of being in terms of two variables, or the side lengths of our base times our height. We can write everything in terms of our side lengths. So we have our volume is s squared times 30s to the power of negative 1 minus 1/4 s. Expanding our parentheses, we can write this as 30s minus 1/4 s cubed. And now from here we can proceed with our usual approach to things, which is to find the derivative first, and that's going to give us 30 minus 3/4 s squared. Well, I'm then going to find the second derivative, and that's going to be minus 3/2 s. And then let's consider our critical values. So our critical values are given to us by solving 30 minus 3/4 s squared equals to 0. So 3/4 s squared equals 30. S squared is equal to 40. And in theory, s could be plus or minus 2 square root 10. However, because we're dealing with lengths, right, the negative solution doesn't really make sense. And so we're really only going to consider s is equal to 2 square root of 10. And now, just to be sure that this is indeed a maximum, if we plug in that value, s equals 2 square root 10, into our formula for our equation for our second derivative, we get minus 3/2 times 2 root 10, which is minus 3 root 10, and the important point being here that this is negative, which means that indeed s is equal to 2 square root 10 is the location of a maximum and we can proceed to find our other values. We can figure out what our height is going to be, and that's going to be 120 minus 2 square root 10 squared over 4 times 2 root 10. This ends up being 120 minus 40 over 8 root 10, and this is 80 over 8 root 10, which is 10 over root 10, or simply root 10. That means that if our dimensions are a height of square root 10 meters and a side length of 2 square root 10 meters, then those dimensions will maximize the volume of our box, which again for your reference is up here. Now, jumping to the multivariate case, right, the multivariable case, you can sometimes take the same approach, right, to rewrite the problem in terms of a single variable using your constraint. But that is often messy, and sometimes it will not work. So a much more generalizable method would be to use the Lagrange multiplier. And the Lagrange multiplier ends up using this formula where f is the function that you're trying to maximize, g is the constraint function, and then you have this type of a relationship where, as a reminder, you have del f, where the gradient of f, which is defined as the partial derivatives of f, and if we're dealing with our x, y, z coordinates, that would be df dx, df dy, and df dz. And we have del g on the right hand side, the gradient of our constraint function g. I'm not going to get too far into the theory of Lagrange multipliers, but pretty much the idea is that any maximum or minimum is going to be on the surface of whatever constraint function, and at that location on your constraint function, whatever value that maximizes or minimizes your function f is going to be tangent to your surface. And then you can leverage the idea of planes and normal vectors to get to this kind of relationship. Well, let's look at an example. If we have this scenario where f is this function x plus 2y plus 3z, which is a line in 3 dimensions, and g is the surface, x squared over 4 plus y squared over 9 plus z squared equals 1. That's an ellipsoid. And the rough sketch of things is actually right up here, where the shape that looks somewhat like an American football is your ellipsoid, right? That's your constraint function g. And you end up having the function f as a line going through the shape, which I'm kind of emphasizing with this arrow right here. Anyways, applying the formulas from above, let's first find that our gradient of f is the vector 1, 2, 3. And the gradient of our constraint function g is x over 2, 2/9 y, and 2z. Now, utilizing our relationship between our gradient functions, we have this. And from here, we can write our first gradient, 1, 2, 3, is equal to lambda times our second gradient, 1/2 x, 2/9 y, and 2z. And then from here we can solve for each of the variables in terms of lambda. So we end up with the 1 is equal to 1/2 lambda x. X will be 2 over lambda. You get 2 is equal to 2/9 lambda times y. So again, y is 9 over lambda. 3 is equal to 2 lambda z, so z is 3 over 2 lambda. Now, utilizing our constraint function, we can plug in and we'll get x squared is 2 over lambda squared over 4 plus y squared is 9 over lambda squared over 9 plus z squared, which is 3 over 2 lambda squared, is equal to 1. Here this is 4 over lambda squared over 4 plus 81 over lambda squared over 9 plus 9 over 4 lambda squared is equal to 1. 1 over lambda squared plus 9 over lambda squared plus 9 over 4 lambda squared is equal to 1. And creating a common denominator, we get 4 over 4 lambda squared plus 36 over 4 lambda squared plus 9 over 4 lambda squared is equal to 1. So 49 over 4 lambda squared is equal to 1. 49 over 4 is equal to lambda squared, and then lambda is equal to plus or minus 7/2. If lambda is equal to 7/2, then x will be, if we consider lambda is equal to 7/2, then we get x is 2 over lambda, so 2 over 7/2, and that's going to be 4 over 7. Y will be 9 over 7/2. And this becomes 18 over 7. And lastly, z is going to be 3 over 2 lambda. and that's 3 over 7. Then, referring to what we did in our prior video, we can figure out the Hessian matrix for our function f. That's the formal method of doing things. We're going to take a slightly informal method here because ultimately the formal method is very, very long and very, very annoying. But if lambda equals negative 7 halves, then x will be negative 4 over 7, y will be negative 18 over 7, and z will be negative 3 over 7. Now plugging in these values into our original function f, which said x plus 2y plus 3z, we can see that f of 4/7, 18 over 7, and 3 over 7 is going to be 4/7 plus 2 times 18 over 7 plus 3 times 3 over 7, and that's going to be 7. If we plug in our negative values, then we'll get negative 4 over 7 plus 2 times negative 18 over 7 plus 3 times negative 3 over 7, and it's going to be negative 7. And that tells us that this first point, 4 over 7, 18 over 7, 3 over 7, is the location of a maximum, and that the maximum value is 7. Similarly, negative 4/7, negative 18 over 7, and negative 3 over 7 is the location of a minimum, and that the minimum value is negative 7. So to kind of summarize what we talked about here, when we're trying to find a relative maximum or relative minimum and we have some additional constraints to worry about, in a single variable case it is fairly straightforward. We can use our constraint function to rewrite the function that we want to find the maximum or minimum of in terms of a single variable, and then apply our test for relative maximum and relative minimum as we discussed in prior videos, referring to our first and second derivatives. In the multivariable case, you can still do the same thing in some situations, but a method that is far more generalizable and is generally much easier to solve for is the Lagrange Multiplier, where you have the relationship between the gradients of your two functions. Typically, f is the function that you want to find the extreme values of, and g is the constraint function, and then as a reminder you have del f, or gradient of f, is equal to lambda, which is some scalar multiple, times del g, or the gradient of g. From there you can solve for lambda, and therefore the location and values of your maximum and minimum values. If you found this content informative, please support the channel by liking this video, sharing it with your friends and family, commenting, and subscribing to the channel. If you're interested in one-on-one tutoring sessions, please follow the link in the description. Have a great day.